If you want to prove a mathematical sequence converges, standard calculus tells you to find the limit. But what happens if the target limit is completely unknown, or worse, impossible to write down? Usually, we measure convergence by watching sequence points march toward a known destination. As the distance between our sequence and that target shrinks to zero, it converges. But let's erase that destination. If it vanishes, how do we measure convergence? We have no finish line. The mathematical solution is to stop looking outward and start looking inward. Instead of measuring distance to a final limit, we measure the distance between the sequence points themselves. This is the foundation of a Cauchy sequence. Cauchy sequences shift our analytical focus entirely. By looking only at internal behavior, we bypass the need for a destination and gain a powerful new tool to inspect the underlying structure of real numbers. Walter Rudin formalizes this in definition 3.8. The sequence is Cauchy if for any tiny distance you pick, epsilon, there is an integer n where the distance between Pn and Pm is less than epsilon, whenever n and m are greater than or equal to n. Let's translate that math into visual intuition. Imagine plotting the points of your sequence. For any microscopic error margin, you can find a specific cutoff line in the sequence. Notice the crucial double index of n and m. We aren't just checking consecutive points. Every single line must be within epsilon of every other point past that line. They cluster inextricably together. Conceptually, as established in definition 3.9, this means the total diameter, the maximum spread of the sequence's tail, shrinks exactly to zero. This gives us the first half of theorem 3.11. If a sequence successfully converges to a limit, its points are naturally forced together. Every convergent sequence is automatically a Cauchy sequence. The pivotal rule is the reverse implication. Look at part C, the Cauchy criterion. In Euclidean space, like the real numbers, every Cauchy sequence converges to a limit. In standard Euclidean space, proving a sequence bunches up on itself is mathematically identical to proving it reaches a destination. It's a perfectly equivalent, limit-free way to guarantee convergence. But do Cauchy sequences always converge? That depends entirely on the mathematical universe you are operating in. Definition 3.12 introduces the concept of a space's completeness. A space is only complete if every Cauchy sequence within it converges. Let's test this by restricting our universe purely to the rational numbers, fractions. Take the sequence approximating the square root of 2, 1, 1.4, 1.41, 1.414, and so on. If we are inside the rational universe, is this sequence Cauchy? And does it converge? The terms definitely bunch tighter and tighter together, so it is a Cauchy sequence. But because the square root of 2 is irrational, that specific coordinate is literally missing from the rational universe. The sequence bunches up, but it has no valid point to land on. It cannot converge. This is exactly why Rudin points out that the space of all rational numbers is the classic example of an incomplete metric space. Cauchy sequences act as mathematical probes. Because they don't require a destination to operate, they easily sniff out structural holes in a given space. Completeness is the defining structural difference between fractions and the solid, unbroken continuum of the real numbers. To lock this in, remember the core mechanic. A Cauchy sequence is defined entirely by internal bunching. The terms get arbitrarily close to each other, completely independent of an external limit. Every convergent sequence is Cauchy, and thanks to the Cauchy criterion, if you are working in the real numbers, proving a sequence is Cauchy guarantees that it converges. But the environment dictates the rules. Completeness is the guarantee that a space has no structural holes, ensuring every Cauchy sequence actually has a valid place to land. Grasping Cauchy sequences is your first step toward mastering the deep internal logic of real analysis. If you're ready to continue deconstructing higher mathematics step by step, subscribe to the channel and we'll tackle the next proof together. To lock this in, remember the core mechanic. A Cauchy sequence is defined entirely by internal benching. The terms get arbitrarily close to each other, completely independent of an external limit. Every convergent sequence is Cauchy, and thanks to the Cauchy criterion, if you are working in the real numbers, proving a sequence is Cauchy guarantees that it converges. But the environment dictates the rules. Completeness is the guarantee that a space has no structural holes. ensuring every Cauchy sequence actually has a valid place to land. Grasping Cauchy sequences is your first step toward mastering the deep internal logic of real analysis. If you're ready to continue deconstructing higher mathematics step by step, subscribe to the channel and we'll tackle the